Sen Plastik adına Teknik İşler Müdürü Sayın Özgür Yılmazel geliyor. Alkışlarınızla.
Thank you. If you don't mind, I'd like to have my presentation in English and hope to finish it in English also. My name is Özgür Yılmazel. I'm the technical manager of Sen Plastik. It's truly a great honor for me to be here as a part of this organization. And I would like to thank PAGEV, the organization committee, and all the sponsors who made this possible for everybody. The plastic industry, as we have mentioned, starting from the early morning, comprises in excess of 27,000 companies and employing over 1 million people. If it were possible to reduce the energy consumption across the industry by 10%, this would result in an annual reduction in carbon dioxide emissions of more than 3 million tons. The industrial processes, burning of fossil fuels, and changes in land use releases gases into the atmosphere, which is called the greenhouse. It is much faster than the natural process. The recent increases in the global average temperature are much higher than normal fluctuations. Today, almost 93% of all the energy resources are entirely obtained from non-renewable sources. This results in a net increase of 10.65 billion tons of atmospheric carbon dioxide per year. Let's see what a carbon footprint is. A carbon footprint is the total set of greenhouse gases caused by an organization, event, or a person. The greenhouse gases can be emitted through various ways, like transport, land clearance, and so on. If you look at the life cycle of the plastics, a waste amount of carbon emission is generated during the raw material procurement, consumption, recycling, waste reduction, and elimination. The average site-specific energy consumption is 2.87 kilowatt hours per kilogram. For thermoforming process, this value is as high as 6.2 kilowatts hour per every single kilogram, while it is only 0.63 kilowatt hour per kilogram in the compounding process. Considering that for every reduction in single kilowatt hour, 2 pounds of carbon dioxide emission can be reduced, there is a great opportunity for the thermoforming process to reduce the carbon footprint by preserving the energy. Let's look at the life cycle of the plastics and the alternative materials. If you compare the plastics with the alternatives, you can still see that the energy consumption demand is pretty much less than the alternatives, but still about 63% of all the energy demand is required by the production. So the question is, how to reduce the environmental impact? The answer is very simple. You have to reduce, reuse, and recycle in every single process of the plastic. In order to reduce the consumption, you have to reduce the waste generation. And there are plenty of different ways to reduce the waste. As you can see here, we can use the enhanced polymers to produce lightweight materials, using compostable polymers to reduce the plastic usage. You can increase the durability of the final product by intelligent design changes. You can increase the production efficiency to reduce the excessive waste. You can use expanding plastics. And finally, you can use always the recyclable raw materials. If you can qualify the material savings, we have 3 aspects. The first one is the quantity effect. It is mainly based on the changes in the amount of plastic packaging or on the material substitution. The second qualification is the structure effect. The structure effect are based on the changes in the structure of the packaging material according to the size and the shape. And the weight effect is the third qualification, which is the result in the weight of the packaging. Between 1975 and 1990, the typical weight of a 1.5 liter PVC bottle fell by 27%, and that of a PET bottle fell by 33%. A typical PP yogurt pot now weighs only 7 grams compared with 12 grams of polystyrene pot in the late 1960s. And the PE bread bags have been reduced to a thickness of 25 microns from an earlier thickness of 40 microns. There are many different techniques to be able to enhance the polymers. The reinforced thermoplastics or reinforced plastics are a subclass of reinforced polymer composites. They can be classified as the reinforced thermosets, reinforced thermoplastics, and self-reinforced polymers. Thermoforming is a viable option to convert the reinforced thermoplastics, for the process has the ability to form large, flat parts of moderate volumes. Thermoformed parts are recognized as having a large surface to thickness ratio. There are some pros and cons of using thermoplastics in the thermoforming process. Since the reinforcing material is often an inorganic in nature, the material requires less energy, less heat to get the forming temperature. This could result in either lower energy requirements, faster cycle times, or both. On the other hand, the reinforcing material may act like a heat sink when forming against a thermoforming tool, possibly negating the cycle time advantage observed during the heating step. Additionally, both the loading percentage and the aspect ratio of the reinforcing material are important when considering thermoforming composite materials. Since an inorganic reinforcing material will not draw or form when heated, both the draw ratio and the sharpness of the relief will become limited as the reinforcement levels increase. Wide range of fibers, ranging from glass fibers to polymer fibers, can be used to reinforce the thermoplastics. You can see here, we can use the glass fibers, carbon fibers, graphite fibers, and carbon nanotubes, and so on. I'm going to give you some examples of these reinforcement materials. One of them is the carbon nanotube enhanced polymers. A nanotube is a hollow cylindrical carbon molecule which has a diameter of about a nanometer. They are grown as multi-volt, single-volt, and double-volt and fibers. Now the CNT, which is functionalized to be used as fillers through chemical exfoliation, dispersion, sonication, and also finally dispersed into the host polymer. As a result, we get a very high tensile strength, high thermal conductivity, high aspect ratio with lower weight percentage loading needed for enhancement, improved elasticity, and high electrical conductivity. You can see the difference between the 5% weight carbon nanofiber and polypropylene and the regular standard PP. Polymeric nanocomposites provide a higher mechanical strength without an aesthetic flaws or deformations at lower densities. Combining the unique properties of nanocomposite and recyclable polymers, lightweight, functional, recyclable, and biodegradable polymers and nanocomposites can be produced. Also, using the porous polymeric compounds, we can further reduce the density while maintaining the mechanical, electrical, thermal, and acoustic characteristics. Therefore, it is a very good alternative technology for lightweight products. There's another technology called the ring opening polymerization, with cyclomer technology-based processing. Ring opening polymerization, it is possible to make low-cost thermoplastic composite with enhanced properties such as lightweight, high stiffness and strength, excellent crashworthiness and corrosion. And the material expansion technology. A roll of solid plastic is prepared for saturation by layering it with a porous material. The roll is then pressurized with a gas such as a food-grade carbon dioxide. The interleaved porous material provides a pathway for the gas to saturate the polymer roll. Once saturated, the polymer is removed from the vessel and heated. As the polymer softens, billions of gas bubbles nucleate in the polymer, reducing the density and causing an expansion. In general, this process increases the length and the width by 150% and the thickness by about 200%. This expansion results in a dramatic decrease in density, typically about 20% density relative to the original polymer initially. One of the latest technologies is the Musil technology. In the Musil technology, tiny bubbles of nitrogen or carbon are injected during the manufacturing process to reduce the weight of the plastic component by 10 to 20% while maintaining almost the same strength. This technology has been successfully applied in the BMW cars to reduce the weight. In 2010, at Sam Plastic, we had made a study with 2 different companies to reduce the weight of the final product while maintaining the same stiffness and the durability of the final product. In order to be able to success this, we have used high-performance nucleators and we have used the enhanced polymers. The product was a 90 millimeter diameter 16 ounces PP cup, which has the height of 125 millimeters. Its original weight was 9.85 grams. The material was a clear PP and the annual production was 50 to 60 million pieces per year. The purpose was to reduce the weight by 10% while maintaining the stiffness and the durability of the product to meet the customer's needs. If you look at the carbon footprint of the polymers, you'll see that the PP has a total of almost 3.5 tons of carbon dioxide emission per every single ton. And the forming and processing contributes for 36% of carbon footprint that the PP causes. After the sampling, you can see a table of our sampling results. The weight was reduced to 8.80 grams, which is about 10.7% less than the initial product. And the cycle time, as we expected, increased by 2 pieces per minute, while other forming values remained the same. We had the same forming pressure, same downholder pressure, and the mold temperature and the cavity number remained the same. Finally, we have a better clarity, better transparency, higher cycle time, and most importantly, less weight than before. If you calculate the carbon emission reduced just by this sampling, by reducing 10.66% in the weight, we had 53 to 63 metric tons per year saving in the raw material. Per every tons of PP, 3.5 kilograms of carbon emission was emitted. So the total reduction in carbon dioxide emission was 183 to 218 metric tons per year. Also, you can reduce the weight of the products by improving the design. As you can see here, there are some irregular shapes which gives a durability and a high stiffness to the tumbler. Even though we're using the less weight than the compared products, we can have the same stiffness and the durability. The products with the unique geometries function with the thinnest gauge possible while still meeting the customer's objectives. So, the lightweight products as a final means the greater fuel economy, low shipping costs, less weight, minimizing the cost, low carbon emissions, low carbon free, and of course, a green world. Thank you.